So, good evening, folks. Welcome to the very first section of the Retrieval and Search Group here at Cohere. I'm Avinab, your host for today. We are excited to kick off with Dr. Weizhi Zhang. I hope I'm pronouncing her name right. The first
Yeah, yeah,
author
yeah.
of the SGCL paper will share key insights on combining self-supervised and supervised learning for graph recommendations, followed by a Q&A. Please join me in welcoming Dr. Zhang. The floor is yours. You can take it over.
Yeah, okay. Thank you, Abby, for the introduction. So br some brief introduction of myself. I'm currently a third year PhD student in the University of Illinois, Chicago, under the supervision of Professor Philby. So, my current today I'm gonna present some of work, including the SGCL, as mentioned by Avinab, and also some kind of related work, also follow-ups, concentrating on more efficient and scalable graph recommendation. And also, I currently transition my research interest in large language model and personalization. If you have any question regarding this topic, you can feel free to email or discuss with me in today's discussion or final conclusion part. Okay, I will directly go through. So here's the basically outline what I'm going to introduce today. Oh, so before we go into the main contents, is the sound volume okay for every audience?
Yeah, you're clearly audible, Vijay.
Okay,
Everyone is,
okay, cool,
yeah.
cool. So the outline today is that we will start from very basic background, including because we assume some of the audience were the new beginners or the search and recommender system domain. So I will start everything from scratch and make sure everyone can get some new information, knowledge from today's presentation. And I will also introduce the self-supervised learning paradigm in the graph-based recommendation. And follow up, we'll introduce and explain our main work, SGCL, in detail, and also illustrate the experiments, especially the data set and the evaluation settings, and final performance regarding compared to other baselines. Finally, we will conclude our work and give further discussion with other related work and follow-ups. So depending on time, some because there's some quite a few slides for the follow-ups. So we're gonna depending how much we're gonna illustrate regarding to the follow-up works. But those are very relevant and interesting work. Okay, before we going start, we would like formally define the what is recommended system. So according to the surveys in the 2019, the ASM Computer Survey, the recommender system actually estimates users' preference on items and proactively recommend items. Oh, wait a second. Proactive recommend items that users might like. So this is more like a formal definition. From my personal perspective, it's more like an information filter system because we have a lot of information from the web. Either we do search or we go into the recommender system platforms like Netflix, Amazon, Instagram in Meta, and also the YouTube. So we can definitely check and see new items. What is a new items really captures our users' interest. That's a key bottleneck of existing recommendation system and ranking system. Um, wait a second. So here the formal definition, and then comes to the first question that why we need graph convolution networks for recommender system. That's pretty as a very basic or say preliminary is that every recommender system platform that their data can form the graph formats or say graph data. Like for example, in the previous slides, we have the interaction from the users and the items in the element. They can definitely form the heterogeneous user item by particle graph. And for the social network in Instagram, we can form the basically users social network. And And basically can first one is that they can mitigate the data sparsity issue. If you look at the left part, so here, uh, actually here is more like a dense graph. We have only 3 users and 5 items. But if we scale up the number of users and items, because basically for those large platforms like Amazon, we have billions of users, billions of items. So if we construct the corresponding agency matrix, so agency matrix is more like we construct the users and then items, we will find that 99% of the elements in the agency matrix are empty. So that's what we call the data sparsity issue. Also the co-star issue, that number of the users and items only have a few number of interactions. So in this case, the user's feedback is very sparse in the recommender system, and the graph convolution can better utilize those supervision signals because you can capture more than one hop neighborhood. By the way, if you have any question regarding to the presentation, so you can just break me and directly pose the question. We don't have to like wait until the last part for the QA session. And the second part is that actually can build up or capture higher order connectivity. So instead, if we look at the right picture plots over here, and we expand the relationship of the graph structure from the user one, and we treat the user one as a root node, and we can actually have 3 hop neighborhoods over here. So basically, after aggregating the information, one hop by one hop, we actually capture those kind of higher order connectivity. So for example, the user one might similar to some kind of other users if we actually capture the similar hop neighborhoods, like some of other nodes, they also have the neighborhood of item 1, item 2, item 3, something like that. So here the graph neural network actually extends the recommender system to capture such kind of higher order similarities. And here's a basic framework of the graph-based recommender system. The first step is to construct the graph. Obviously, as I just mentioned, we form the graph structures. But basically, in the industry platforms, we have very, very large scale graph. So we might need the pre-processing, like we split different kind of clusters. But here we just gave a very simple one, or say we define a research problem, and we just directly construct the graph, the user item graph, based on their interactions, and also the agency metrics. And the second step is do the message passing for graph convolution. So here is actually the graph convolution based on neural networks. And the more recent popular paradigm or graph convolution is more like we do light graph convolution, that we do not use any neural network, we just do aggregation and message passing. But here is just like a overall framework. And after the aggregation of the different layers, as we can see here, we have layer 1, layer 2, layer 3. It's actually we capture the information from 1 hop, 2 hop, and 3 hop. So in the general setting, we configure the number of layers. It's like mostly in 3 layers or 2 layers, because if you stack more layers, you'll find that the performance will gonna drop due to the over squashing problems, such kind of things. It's well studied in the graph community as well. And finally, we will obtain the node representation for the users and items, and we just calculate the final score. Either we do the dot product or some kind of other neural network transformation. And anyway, we will obtain the final ranking score of the user and the corresponding item. So first we need to do training, but after doing training, so in inference stage, we will have the ranking score of, let's say we have user 1, and we have already interacted item 1 and item 3. So basically, the other rest items will be on an item category, and we will rank based on their ranking scores. And we can see, so sometimes their item 4 might achieve higher ranking score, and we will So in the real world ranking or say recommender system, the item 4, item 5 will pop up in front of the other items. So any questions so far regarding to the background of recommender system and the graph-based recommender system? Any questions for this one? Just feel free to ask any kind of general question as well. Okay, it seems very clear over here. Now we need to go through a little bit more deeper into the self-supervised graph learning paradigm. So this is called self-supervised graph learning for recommendation, and this is one of the first work that introduce the key idea is introduce graph recommendation and contrastive learning, which is also kind of a self-supervised learning into the graph recommendation. So I think this work's already gained more than thousands of citations, and it's kind of fundamental work in this domain. So the general idea is pretty simple, that it adopt, as we just mentioned in the main pipeline, we have the graph structure, and we have the graph encoder, like any kind of form, and we pass the graph structure information after graph encoder and obtain the final 2-hop, 3-hop node representation, and finally do the ranking and recommendation. So that's the original one. So based on this kind of framework, the self-supervised graph learning actually add up one more step or one more optimization process, which is called contrastive learning. And pretty much like the contrastive learning in the graph community and also the computer vision task, we have to do the data augmentation. So in the graph-based recommendation, we perturbate edges or perturbate the nodes, or sometimes we do random walk. So anyway, we need to destruct the original graph structure, and we want to maintain the similar representations even we do those kind of modifications. So here we basically have two extra graph encoder to obtain the positive and either the negative contrastive pairs. So here is a more like a typical example of the loss computation, the user side of graph contrastive learning, and we will also have the item side, add them together to obtain the final graph contrastive learning loss. So based on this graph contrasting, we have number 1 to control the weight of this contrastive loss, and this is more like a hyperparameter we can adjust during the experiments. But I will illustrate later how these kind of things will affect the optimization problems. And we have the recommendation loss. This is typically the PPR based personal ranking loss, which is very popular in the ranking tasks. And we have number 2, which here is another hyperparameter to control the normalization of the original weight. So we just make sure it's not optimizing too much. It's more like a regulation part. And this is for the first work. We call it self-supervised graph learning for recommendation system. And the second work is called neighborhood enriched contrastive learning for recommendation. The basic and or say the more meaningful part of this work compared to was the first work called SGL. SGL. The NCL is more like we want to find more meaningful neighborhoods. So here, I think the major contribution of this work is what they call the semantic neighborhood. Their structural neighborhood, their main components actually have 2 parts. They have structural neighborhood and semantic neighborhood. Their structural neighborhood is more like we have some kind of users, and we want to have some obtain other users which actually shares a similar search structure or very close to each other. So they want to find other similar users as well. And for the items, also want to find some kind of structure or closer items doing the optimization. And for the semantic neighbors is that we first train based on the traditional graph optimization or BPR loss, and then we're gonna find some kind of neighborhood based on their well-trained embeddings. and they call it semantic neighborhood, and they use a KNN optimization process to find those neighborhood as well. So that's their main contribution. This is also a kind of early work published in the TRW web conference in 2022. Yeah, and personally, I think their main contribution is more like a semantic neighborhood over here. But it also takes more time and also computation resources doing the optimization because they are all the EM optimization. They have to find the prototype, also the clusters for finding the semantic neighborhood. And there's a lot of hyperparameter as well. Like for example, you have to define number of the cluster, number of prototype. So sometimes you have no idea if you got a new data set. So this is more like an extra effort when doing optimization. Another work is called a more recent work is called simple graph contrastive learning for recommendation. Here, their idea is pretty simple but very strong. That they pose a very key question that and also challenges the necessity of graph augmentation. So as in the two previous work, actually we can see that we do age drop or random work or no drop, or sometimes we do augmentation to find the prototype of the k-nearest item. But in this work, they first conduct the preliminary experiments and find that okay, so SGL is the first work we call SGL, and ND is no drop, ED is age drop. And we can find actually, although the age drop gains the strongest performance, but the SGL without augmentation actually achieve very competitive or the second best results, very close to the SGL with age drop. So we can find that actually, or the author posed the question that do we really need graph augmentation, and also highlights in this work they also highlight the importance of uniformity while proposing a very simple and noise-based augmentation method on the right part. They're basically adding more noise doing for their node embeddings, and this kind of noise will propagate through the graph convolution. But their ultimate goal is that doing a contrastive loss optimization, you still want to maintain the original representations. So this way actually kind of make their embeddings more distributed or uniform. And here I would like to illustrate existing or challenges of existing work. The first one, what we call is the conflict ingredients. So as we already mentioned in our introduction or previous related work, that all existing methods actually relies on the multi-task learning frameworks and actually requires predefined hyperparameter. No matter what specifically the methods are, they have bunch of hyperparameters, especially the one they have to balance the BPR loss as well as the self-supervised learning loss. This is actually key hyperparameter. They have to adjust very carefully during the optimization. So mostly they will grade search from 0.1 to 0.5, something like that. And the second problem is that we have the inefficient graph augmentation because as we mentioned in the first plot, we actually have two more extra graph encoder doing the optimization process. And these two more graph encoding process actually takes much more longer time compared to a single one. And if the number of nodes, let's say the number of users and items increase or to the billion scale, that will be a big trouble because basically the complexity will also increase exponentially. And for SGCL, they have the randomized graph augmentation, as I mentioned, and NCL, they have unsupervised k-means algorithm to find the semantic neighbors. And all for SimGCL, they have randomized and unsupervised noise. Some might hurt the representation as well sometimes because during the experiment, I find that SimGCL is quite unstable here. And our goal here is quite simple. We want to unify the base personalized ranking and self-supervised learning laws to avoid conflicting ingredients, because they also have a multitask learning process. They have a hyperparameter to balance the BPR and SGCL loss. We want to unify these two type of loss. The second one is we want to do efficient training without time-consuming data augmentation. As we just mentioned, every time if you have a graph notation in their framework, they have to construct the corresponding to graph encoding process to pass it every time if you want to do batch training. That would be a major issue doing the online optimization, especially in industry scale graph representation. And our solution is quite simple and straightforward. That compared to the left side is more like a traditional one. We have the graph encoding process. The blue one represents the BPR loss, and the red one represents the graph contrastive loss. So they have a perturbation on the edge and do the graph convolution. But our supervised graph contrastive learning loss is that we do not want to modify any graph structure over here. We do augmentation free, and then conduct a graph convolution directly calculating the supervised graph contrastive loss based on original graph. So we have here the pipeline basically unifies the BPR loss because we design the supervised graph contrastive loss, and which we'll illustrate later, and we conduct very efficient training without any type of augmentation. And if we look at the original photo of the user one, actually we have the lightweight graph convolution that the K1 is more like a next layer representation. Every next layer representation is based on the prior layer, and we have an aggregation process. Okay, hi, George, you have a
Hi
question?
there. Sorry to interrupt.
Yeah.
For slide 9,
Mm-hmm.
I didn't really fully get. I know it's the summary slide, but could we spend 20 more seconds on it, please?
Yeah, sure. So can you mention that which part you are still confused, like regarding to, or you want to know more detail regarding to the pipeline?
Yeah, please, the second one.
Okay. So basically, compared to the original, the self-supervised graph contrastive learning loss, as well mentioned that we have three types of graph encoder, right? So the first one, second one, third one. The second and third one is more like a focus on graph contrastive learning, that we want to generate a new type of a nodes representation. But here we can see that we only relies on one type of graph convolution, or you can think that we just rely on the first one. We just adopt one type of graph convolution. But the difference is that we apply the graph contrastive loss directly or injecting or combined with a traditional BPR loss. So we just have one pipeline over here. So kind of remove all this rest of graph augmentation as well as a redundant graph encoding process. Yeah. So
Right,
what you can
so
think is
it's
that we
actually more efficient, huh?
we move the graph contrastive loss into the representation loss and remove all the graph data augmentation part. Yeah. Is that clear or? Okay, cool. Thank you. Thanks for the question. And we have lightweight graph convolution process here. The key is basically you can think of like a prior node representation. The first hop, or let's assume this is like the first hop, and then the K plus one will be second hop representation. So basically, sometimes we aggregate to the third hop, obtain the third hop, and finally the node representation, like we do average or have a weight to combine all the previous hop, one hop, two hop, three hop over here. And then we also have the limitation of multitask learning, MLT, that we mentioned before, that we have the recommendation loss and the hyperparameter to control the weight of graph contrastive learning loss. In different data sets, it actually applies extremely different lambda over here. And our solution is actually to inject the supervision directly into the graph contrastive learning laws. That if you find during their influencing laws that we have the augmentation dot prime, which is like one type of augmentation, and user I with double prime is more like a second graph augmentation. They want to minimize the difference between the same nodes with different kind of augmentation versions. But our motivation here is that we want to directly align the user and items and distribute all the users and users and also items and items. So if we want to minimize the loss, we want to actually is to maximize the distance or dot product result of user I and item J, and also want to minimize the result or score after user I and other nodes of in the batch compared to user I, and also the item J compared to other items with item in the batch of the item J. And here is a comparison of the. Hi.
Hi, can you go to the slide 9?
9. Okay.
Oh, no. The one you were explaining about the loss
Oh,
function.
this is
So here, what is the UI dash represent? It's the item augmented version I dash, or what's that?
you mean which kind of equation?
Yeah, the bottom one. Is it
The
related?
bottom one.
Mhm.
So basically, the UI here is represents the representation of the user, and VJ is more like a connected items. So let's say if we have the user 1, the VJ could be item 2, item 1, or item 3. Yeah.
And the bottom denominator one is like all other items, right? If I'm understanding correctly.
Yeah, in the batch. So if we have the user 1 as user 1 as UI, and UI will be all the rest user, like on not something like user 2, user 3, but something others in the batch, which is actually regarded as negative samples, because you want to differentiate like different users. That makes sense, right? You want to differentiate items from different items, so you can have a better ranking. And this also aligns with the uniformity in the previous paper. This paper, they also concentrate or highlight uniformity, that we want users and items to be more distributed, or uniformly distributed. Yeah.
Thank you.
Yeah, cool. Good question. Yeah, and here we have analysis compared with the traditional self-supervised learning laws and SGCL laws. So if we here will hold a strong assumption that if we can't reach the perfect alignment, the perfect alignment is basically saying that if we have the user 1 and we observe that user 1 has already interacted with let's say item 3, we hope their distance or dot product score of the normalized embedding will be 1. So we assume they have the normalized the perfect alignment. So if we hold this assumption, we can derive some kind of conclusion that over here we can see actually the optimization process of the SAO rack, which is self-supervised with BPR loss. They want to also to minimize the score of the user 1 item, which basically means you want to differentiate the users and negative items. That makes sense for most cases, but if we have some kind of false negatives, so for example, in their negative sampling of the BPR loss, we have to sample sometimes unobserved items, but sometimes the unobserved items are not the real negative items. It's just never seen before. So there exists actually a large amount of samples over here. But if we do negative sampling or false negative sampling over here, they will largely affect the final optimization of the self-supervised loss over here. They actually want to or say push the user representations and item representations away. And we have some follow-up work to do some visualization on the representation space and also find this kind of similar effects. But that result will be posting the final discussion part. And anyway, we can find after comparing the self-supervised laws and SGCL laws, we identify the key bottleneck from the optimization process itself. And here we want to analyze the time complexity and compare three type of works: the LightGSN, which is a previous SOTA of graph-based recommendation system, and also SGL, the first work we mentioned, most fundamental and preliminary of the self-supervised graph learning. And we can see here, if we have the number ages, probability, number layers, and embedding for the batch-wise time complexity, we can find that doing the agency matrix, actually, the SGL, the self-supervised, actually contains approximately 2 more times compared to the original LightGSN and SGCL, and also for the cases of graph convolution. But actually, these two parties consist of most of the time during the training sometimes, and they have also the extra sampling process due to the BPRs. As I just mentioned before, they have negative sampling process, and our SGCL actually alleviates all the process. And for the GCL loss computation, as we can see, we actually have the B square, but actually the B square is not that important because we have batch-wise optimization in in the GPU. So in general, the SGCL is pretty much efficient. And here's the experimental setup. We compare different baseline, including MF model, graph-based model, and self-supervised graph models, and evaluate on 2 types of Avinab dataset. And as we can show here, we actually show very strong and competitive performance compared to all the baseline in terms of ranking, NDCG, and ranking either on top 20 or top 50. And we have also conduct experiments regarding the trade-offs between efficiency and the performance. Like for example, we have along the x-axis, we have the average training time per epoch. And we also on the y-axis, we have the performance, the NDCG at 20. And we can see that SGCL actually achieves the best performance while maintaining very efficient computation resources, like average training time per epoch, compared to like the very naive or simple naive models like base MF and neural MF, better than any kind of graph-based model, as well as other self-supervised model. And we also find the total number of time over here, SGCL, doing such kind of small scale dataset training. And here's optimization, also convergence speed. And we can see that the SGCL actually converges really, really fast on the first few epochs. So basically you can stop at epoch 5 stuff, and you already achieve good performance. But for the LightGSN, it's like just increase very, very slow, and you have no idea what you're gonna stop. Probably 50 or 100 epochs. So here we want to give a conclusion regarding to our framework, that we have designed efficient framework by pinpointing the ineffective optimization as a bottleneck of prior self-supervised graph recommendation system. And we designed a streamlined framework to eliminate the redundant graph convolution and complex graph data combination, making this one very efficient. And we also develop a very novel loss that theoretically allows and introduce this kind of loss to integrate the training of self-supervised as well as the supervised loss into a single object function. And finally, we conduct a very comprehensive evaluation on the real-world dataset to testify the effectiveness of this GCL from different aspects. And each actually achieves the highest ranking score with remarkable low training time. Yeah, that's all for the SGCL itself. And we actually have some follow-up, but just briefly I will gonna briefly introduce them depending on the time. But until now, do we have any question regarding to the
Uh,
firework?
Hi, not actually question. I just want to understand the intuition behind your proposed methodology. So basically, in the
Mhm.
slide 9, as as you showed, like uh, I just showed like in this self-supervised graph. So I do have very less knowledge, so I might be saying something wrong. So
Mhm.
I'll be really happy if you correct me. So in this cases, like there's we needed 3 graph encoders to get the graph representation or node representation. So this approach is like combining the recommendation loss and graph contrastive loss. So you
Yeah,
want
yeah.
to reduce the efficiency of
Mhm.
need of using 3 encoders. So you use this graph, just use a single encoder, and from there you are trying to combine this graph contrastive loss into a single loss. Is that correct?
Yeah, yeah, yeah. You're
And
correct.
when you say augmentation free, here augmentation free means the spread out version of the graph, right? Or is it different?
The augmentation phrase that we do not do perturbation on the original graph. As you can see over here, we just apply the contrastive laws. So
Mhm.
typically, graph contrastive laws or contrastive laws requires a negative sampling. So
Ex-
it naturally asks you to do data augmentation. But here we do not data augmentation and adopt a very straightforward way that we consider the user and item as positive pairs. So original one, they have to do data perturbation or uh, or say the A dropout or no dropout to change the graph structure and obtain the new representation of the same nodes. Like user one, we obtain two types of augmentation way, and one is the positive sample one, and
Mhm.
another augmentation will be the positive sample two. So in our way, we actually directly adopt the positive pair as using items, kind of alleviate the effort for data computation.
So basically, what you're trying to say is like in the left side, we have like part out version, but we do not use the part out version. And for the graph contrastive loss, we need a negative samples, but the negative samples are directly used. Like for example, if user one and user two has connection, then that's a positive sample. If there is user three where user one do not have connection to user three, then that is represented as negative example, and
Ye-
that is considered as contrastive loss. Uh, from
Yeah,
the
yeah. The formulation is like something similar, but I have to correct that we have positive sample that of the users and items, not user and users.
Mhm,
So our positive sample that if the user one directly interact with item three, we
mhm,
consider this pair as a positive pair.
mhm.
Yeah.
Oh, so then if the user one do not have any relationship with item two or item three, then you call that as a negative sample, and that is used
No,
in the
no, no,
contrastive loss.
no, no. So the positive pair is that user and items,
Mhm,
but for negative pairs, we consider it user and users. That will make more sense as because when we derive the interactions, we
mhm.
actually do not want to put user and item in the negative pairs. We want to avoid this problem. So in our negative samples, we only have either it's all users or
Okay,
all items. And for the positive pairs, we have these items to connect users and items distributions.
okay, thank you.
Yeah. Actually, we have a follow-up work called mixed GCO, which actually we have the visualization distribution, as you can see over here. The SGCO and the follow-up mixed GCO, like we have the augmentation version or say extension. And prior work actually do have a misaligned distribution because they have a central uh, distribution or kind of distribution or subgroup, which alleviate or deviate from the original mean distribution, as you can see over here, and also leads to poor performance regarding to many of the beauty toys and also yield data set. Yeah. Okay, any questions so far? Cool. I just briefly, due to the time limit, I just briefly introduce are some of follow-up work or related work for the efficient and scalable graph computation. So based on the SGCL work, actually we have already developed very simple, streamlined pipeline for using a self-supervised loss. But for the graph recommendation itself, we actually still relies on graph convolution during training. That we still have one graph encoder doing training. So the follow-up question is that do we really need those kind of graph convolution? And also, our SGCL only focus on the okay, we directly remove the data augmentation. But in most scenarios, like computer vision, NLP tasks, the data augmentation is still very important, but just lack of very efficient graph augmentation. So what if we build more efficient and more supervised, inject more supervised signal into the graph SGCL? That's the second question. And the third one is that with the popularity of large language model, how do we like effectively utilize the large language model embedding stuff? That's all the question around this SGCL and follow-ups. So let's just introduce them one by one. And the first one just we mentioned about the how do we do data augmentation based on SGCL. And here's a framework. Actually, we devise age level mix-up as well as a node level mix-up based on original SGCL framework. So the benefits of this mix-up for supervised augmentation is actually we do not change the overall structures of like we only still relies on one type of graph encoder. We don't have 2 or 3 type encoder, but rather after the graph convolution we do the mix-up. Like on the representation space, we can see. So compared with the original SGCL loss, like user 2 and item 4, or item 4. We actually, after the node mix-up, we have the user 2 of item 4 on the edge, and also the user 2 item 4 with a bar. So along their line, we have the edge mix-up, and around the users and items, we have node mix-up. Node mix-up here is more like a mix-ups according to different hops of layers, but edge mix-up, we directly mix up according to the user items along their lines. So this will make their supervision store augmentation more obvious during the optimization. Also contributes to the final performance as well. Yeah, that's one of the follow-up, and also for some kind of data sparse scenarios, we can find that mixed GCL actually achieves very strong performance in those data sparsity. If we reduce the half of the interaction in the training data, that's pretty much obvious. And especially compared to SGCL, actually in those scenarios we have a very sparse very sparse data. It actually shows a lower performance compared to LightJSON, but mixed GCL still gains stronger one compared to the SGL. SGL is the first one. They just do data augmentation, randomized one. And according to the graph convolution, we also have a work like GOD, which question or challenge the necessity of graph convolution during training. This is more like an interesting work. We have conducted some preliminary study and experiments and investigate, okay, now we actually do not need graph convolution during training. We just do post-training graph convolution, which will be achieved very competitive, like 95% compared to the original one. We remove all those graph convolution process during training, still maintaining high performance with lightweight post-training graph convolution. And both days, we also did some kind of further experiments, investigating the trade-off between embedding description and the higher order information after the post-training graph convolution process and operations, and also devised the light post-training graph ODE, which is also published in CIKM last year. And we have the skip all the graph construction, graph encoder process, doing the optimization. And then we do for the post-training or inference stage, we have ordinary differential equation for dynamic node representation modeling. So this is also very efficient in terms of overall pipeline. And we have show that it shows very, very strong competitive performance regarding to other graph-based line and also direct AU with new type of loss functions. And here's like convergence speed and optimization. So light GOD actually achieve very close performance to those kind of MF-based model. And final one is that we investigate the logic model part, that we identify the embedding class issue. Like, for example, in large language models, we generally have very large embeddings, like more than 4,000 or 8,000. Compared to the recommended system models, we just take 128. That's a typical configuration for the embedding size. And if we enlarge the embedding size, we find that although the number of parameters increase largely, but the performance will drop sharply as well, especially in an office data set. And here's what we call embedding collapse issue. So we naturally pose the question that how do we harness power of language model for recommendation in an effective and scalable manner? And this is the motivation of this work. And we basically do a selective initialization, that we first have some texture information of the item and process to some pre-trained decoder-based language model or encoder-based large language model, and then do several types of selection strategy, like uniform selection, like k equals 0, 3, 6, and also just random line selection. Or finally, we have the variance-based selection that just rank top k with high variance value. And finally, we have observed that it shows very consistent and strong performance no matter what kind of architecture it is. And the the graph-based model, SGCL, which is a self-supervised graph recommendation model, and SGCL, which is our work, the supervised graph contrastive learning method. And we find that especially on SGCL, it can show very strong performance gains in those kind of co-star scenarios. And we also compare with large language model-based recommendation system. Like in terms of parameters, it's demonstrate very, very efficient computation resources and also stronger performance regarding to those large language model-based recommendation systems. And here's a recap of all what we have discussed today. We have discussed the SGCL, one of the recent work published in Recommended System 2025, that we eliminate complex data augmentation and unify the supervised and self-supervised tasks in a single object function. And we've also introduced the follow-up work, mixed GCL, which introduced a novel no-level and edge-level mix-up to augment the original user item by polygraph. And for light GOD, we actually we are the first to challenge the necessity of graph convolution and develop very efficient post-training graph convolution framework along with continuous graph ordering differential equation, allowing the dynamic modeling of node repetitions. And finally, for the LM init, we identified the embedding collapse issue and propose a new paradigm how to effectively leverage large language models for the collaborative filtering embedding initialization, and also propose 3 types of strategies for such kind of scalable language model-based recommendations. Okay, that's all for the presentation today. Any questions regarding to any of prior work?
Hi, can you hear me?
Yeah, hi.
I just wanted to, I guess, get another explanation. How exactly, I didn't quite understand how exactly you use the LLM to create the embeddings.
Okay, that's cool. So basically, the existing structure of the let's see. The existing structure of the large language model is either encoder based or they have encoding decoder model. But I think people nowadays don't have this such kind of structures. And more popular parameter is called decoder based model. So for those decoder based model, we have the next token prediction, one step by one step. So for this kind of decoder based, we have currently we have a very strong baseline or benchmark to evaluate like multilingual just based on the text embedding, and they also have a benchmark for multimodal. So I think there are different kind of structure. In general, the new pipeline or baseline for the decoder based decoder based large language model, originally they cannot directly generate the embeddings for the whole sentence, but now they can do that based on those evaluation on the benchmark, and also they have a configuration that you can directly do a sum up on the next token prediction on every tokens. Like for example, we have the title, and then we calculate the embeddings, and then big chapel. So basically, for every next token, we have we have to calculate final embedding for next token prediction, and finally just sum up it or do the average. And finally, they can get up the corresponding whole sentence representations. But for the encoding based model, they just directly go pass through like a bird. It's more like a encoding based model. We just go pass through all the transformer, and then we'll get the corresponding representations. Yeah, it's more like a free lunch from the large language models. But we want to investigate how to leverage those embeddings, because those embeddings are generally very, very large.
Okay, that makes sense. Thank you.
Yeah. And we are already identified that that makes sense if we use large embeddings in the recommender systems.
The
Okay.
section was amazing, Weizhi. I
Oh,
learned a lot.
cool.
Yeah.
Cool. Thank you so much.